Okay, so for our final lesson for Unit 5, we're going to talk about how quadratics and square roots are inverses. So first, kind of a little bit of old information. Let's say we had something like f of x equals 1/3 x plus 1. And we wanted to find an inverse of that. So we had distinct steps when we were looking for inverses. What we typically did is we replaced f of x with y as our first step. Then we switched the x and the y. I'll move the mouse for you. And again, all I'm doing is literally switching them in their locations. And then finally, we would solve for y. So in this case, I'd subtract 1 from each side, giving me x minus 1 equals 1/3 y. And then finally, I'd multiply both sides by 3. So I'd get y equals 3x minus 3. This would be our inverse. In inverse notation, we would have written that as f inverse with that little -1 as 3x minus 3. So that was the process that we talked about much earlier this year. That was the process we talked about, or you should have talked about in Algebra 1, maybe 8th grade math as well. Just this general of finding something that inverts or undoes something else. So let's take a look at our basic quadratic then. So let's go all the way back to our y equals x squared. So from last unit, and again from Algebra 1, when we graphed y equals x squared, we had something that looked like this. 1, 2, 3, 4. 1, 2, 3, 4. Now, when we talked about inverses, we said there's several ways we can go about it. So we just kind of reviewed the process algebraically for finding an inverse. But there's also a process graphically. So we said if we graphically wanted to look at an inverse, what we'd do is we'd be doing a reflection through the line y equals x. So if I were to take this graph and reflect it, I would actually get something that looks like this. This would be our inverse. Notice that the whole thing is mirrored across that line. If I put it straight up and down, you can see it a little bit better. The left is the same as the right. So we've reflected y equals x squared through the line y equals x, and we've gotten this. So let's apply that inverse idea to our basic parabola then. If we have y equals x squared, and we wanted to find our inverse, well, we'd switch the x and the y. So that'd give me x equals y squared. And then we'd solve for y. In our last lessons, when we talked about solving things like this, we had discussed using square roots. And we get y equals plus or minus the square root of x. This kind of thought's going to be important. When we look at the plus or minus, when we graphed square roots, let's kind of look at what each of those does. If we graph our basic old parent graph, y equals square root x, or the positive version, 2, we get this guy here. If we graph the negative version, here's my y equals square root x. If we graph y equals negative square root x, we get this one instead. And the reason we kind of make this distinction goes back to our function notation. Y equals x squared is a function. It passes our vertical line test. But as soon as we flip it, it starts failing the vertical line test. So the inverse is not a function. And in point of fact, that's one of the first things that we're going to have to look at, is how can we make sure that this ends up being still a function? And the answer is the only way you can really do that is by restricting domain. So let's do our first of 2 quick examples at looking at restricted domain. So let's say we had something that looks like this. This would be y equals x squared plus 2. But we're only looking at this part right here. We're only looking at a specific domain of x has to be greater than or equal to 0. By chopping a parabola in half, we can actually restrict it so that the inverse is going to be a function. Now, the key when we look at this is we need to know which side. So if I go to find the inverse, I'm going to take this and apply my inverse to it. So x equals y squared plus 2. Subtract the 2 from each side. I get x minus 2 equals y squared. And then I would need to square root it. And the question you have to look for is it going to be the plus or is it going to be the minus? So we want to think in terms of mirroring it. So my graph of y equals square root of x minus 2 shifted right 2 units. It's starting there. To be mirrored, I need it coming up. I need it to look like that. So we can see that we're getting that nice mirrored effect visually. So to do that, I need the positive version. I need the positive x minus 2. As a flip side of this, what if we had a graph that looked a little bit different? What if instead we were only looking at, say, this graph here? The negative half of y equals, let's see, this would be x plus 1 squared, but we're only looking for x is less than or equal to negative 1. If we're only looking at this portion of the graph and we wanted to do the inverse, we'd still do the same process. So I'm going to take my equation, switch the x and the y's. So I have y equals x plus 1 squared. Just like in our previous lesson, to solve this, I'd now take a square root. We get square root of y equals x plus 1. And I'd subtract that 1. Oops, I forgot to reverse the x and the y's all the way through. Now see, that's what you get when you don't pay attention. Remember, you got to switch the x's and the y's. So this would be my function. The question is it the top one or the bottom one? So when we took that square root, it has to be a plus or a minus. But we need it to actually work. We need it to know which one it is. So because our domain is restricted to this side, graphically, again, if I looked at it, if I were to draw square root of x minus 1, starting here, if I were to draw the positive version, that would not mirror. It doesn't work. In fact, I need the negative version instead. And that will give me my actual mirror image coming down. So my actual inverse is negative the square root minus 1. So as you go through and you work algebraically, be careful. It's often going to be helpful to think in terms of a graph as to what part of it that you actually need when you solve. Are we going to need the positive side or are we going to need the negative side? All right, so let's just kind of do some general practice with it then. So how about we have a function f of x equals the square root of x minus 1 plus 3. And we want to find the inverse of that. So again, think in terms of graphing, and we want to be careful. So if I just to sketch this, that's the square root of x that's been shifted 1 right and up 3, 1, 2, 3. So graphically, this is looking something like that. So when we find the inverse, we only want to find the part that's going to correspond to that. It doesn't make sense to do the whole thing. So again, I'm going to run through my inverse process. My y equals the square root of x minus 1 plus 3. I switch the x and the y. And I solve for the y. So we'd subtract 3. So it gives me x minus 3 equals the square root of y minus 1. Now I need to square both sides to cancel out the square root. Gives me x minus 3 squared equals y minus 1. And notice I'm not going to FOIL it out. It's honestly going to be easier if we leave it in like this because it's going to become vertex format. And then I can finally add the 1 to both sides. So I get y equals x minus 3 squared plus 1. So this is a parabola that's moved right 3 units and then up 1. 1, 2, 3, and up 1. But we don't want to draw the whole parabola because we only need the portion of the inverse that makes sense. So here, we need the portion that was coming this way. So to match it, we're going to need only the portion of the parabola coming that way. I don't need the left half. It's not part of it. So if we were to talk about domain and range, let's kind of look at that. In my original function here, our domain would be from 1, to infinity. My range would actually be from 1, 2, 3 to infinity. So we started up here, went 1, and then to the right forever, started at 3, went up forever. If we were to look at this picture down here, and we looked at our domain and range of this, notice that the domain here is 3, and it went to the right forever. My range was here at 1, and then went up forever. And this is actually the pattern that we should see. Inverses are kind of the opposites. Remember, x and y, but part of our inverse process is switching x and y. So of our original function, the domain, when we did the inverse, became the range. The range became the domain. It flip-flopped. So be aware of that as you go along. All right, so we talked about finding in the inverse. It's just the same process that we've done before. You're going to start with the original equation. You're going to switch it with the x and the y's and solve for y. That gives you the inverse. That same basic process we learned so long ago, it still applies. The last thing, and again a review, is how do you prove that something's an inverse? So let's say that we had two functions. We had f of x equals x squared plus 7, and we had g of x equals square root of x minus 7. In order to show that two things are inverses, or to prove they're inverses, we had to do the composition of functions from way back when in this year. So we have to show that f of g of x ends up all canceling out to just x. And we have to show that g of f of x all cancels out to just x. It has to be true for both. That was our rule when we talked about inverses. In order to show that two functions are inverses, that have to be, both compositions have to cancel out to just x. So let's take a look at these and actually see, are they inverses or not? So to find f of g of x, I'm going to take g of x and I'm going to put it inside f of x. I remember the other notation that we used was sometimes this one, and that meant the same thing. So again, so f of g of x, I'm going to take g of x, I'm going to stick it right inside of f of x. So f of g of x, that is f of, my g of x is square root of x minus 7. Okay, so now I'm going to stick that right into there. So it was x squared, so that is square root of x minus 7 squared plus 7. So I've stuck g of x completely inside of f of x. If we simplify this, the square root and the square cancel. I get x minus 7 plus 7 is just x. So it worked in that direction. F of g of x is just x. Now, but to prove that it's an inverse, we have to do both directions. So now I'm going to flip it. So now we're going to g of f of x. In order to do this, we're going to take our f of x and put it right inside. So that's g of, my f of x is x squared plus 7. So I'm going to take my x squared plus 7 and put it directly into the function. So that's the square root. Oops. Yeah. The square root of, I put in my f in terms of x, that's just x squared plus 7, and then minus 7. So that's the square root of x squared plus 7 minus 7. The 7's cancel, I have square root of x squared, and it again cancels right down onto x. So this is how we can show that things are inverses. The process did not change from when we were doing work much earlier this year, or when you did inverses in Algebra 1. Instead, we just kind of look at it and we have to apply it to the fact that square roots and square powers cancel out. That's really the only thing different in this part. All right, probably the most difficult part of all this is just looking at graphs and figuring out what is happening to domain, what part of the domain you need. So just be careful with them. Graph it out, look at it. Do you need the top half of it? Do you need the bottom half? Do we need just the left or just the right? Or can we use either one? So just kind of think your way through, draw them. Actually think about what it'll mean as you do the work.